we talked about how astronauts will pilot the space shuttle orbit. Today we're here at the Neutral Buoyancy Lab at the Johnson Space Center to talk about weightlessness, how to simulate it on Earth, and how astronauts can train to live and work in the outer space environment. We're going to go talk to astronaut Dan Burbank to learn some more.
Hi Misha, it's good to be here talking with you today. My name is Dan Burbank. I'm a Coast Guard helicopter pilot turned NASA astronaut, and been at NASA for about 10 years, since 1996.
So when you're in space, do you have weight or do you have mass?
We always talk about being weightless in space, and in fact we don't have weight, but we have mass. That's the bottom line. We still have mass.
So first we need to talk about the difference between mass and weight. Now mass is a measure of how much stuff there is in an object. Everything's made of mass. You, me, the air that we breathe. And mass is measured in kilograms. Now weight is a measure of how much force mass exerts on an object. Now this mass in particular, 200 grams, when put on a scale, will bring the needle down a certain amount. Now that is measured in newtons. So mass turns into weight because of gravity. Now gravity is what causes two objects to be attracted to one another. It's what causes us to stick to the ground instead of floating away. Now, most of the time on Earth, you feel the same weight all the time. However, there are times when you feel a different weight, like when you're in an elevator. When you're first in an elevator and you're going up, for the first couple seconds, you feel heavier as the floor pushes you up. Now you feel lighter on your way down, as the floor is literally pulled out from under your feet. An extreme example of this is the Tower of Terror at Disney World. Now we're going to show you in an experiment here what it's like when the floor is totally pulled out from under your feet and you're in free fall. All right. So here we are at our free fall elevator experiment setup. Now we're going to put the scale here and our 200 gram mass from before. Now as you can see, the needle reads at 200 grams. Now watch what happens to the needle as we pull out this giant toilet paper roll and the platform goes into free fall. We've looked at weightlessness and how we can simulate it on Earth. Here are some cool things you can do with it in outer space.
Really no way on dry land in normal conditions to be able to practice a spacewalk, with a suit and you as a system weighing so much. So the only way we can do it is basically take advantage of something that a Greek scholar an awful long time ago sorted out, and a fellow by the name of Archimedes.
Neutral buoyancy is a condition where an object has an equal tendency to float and to sink. Now buoyancy is the force that keeps an object afloat, like a ship. When you add too much weight, it causes the ship to sink though. As you can see, this weight sinks. This piece of plastic floats. The right combination of the two let the astronaut that's training hover in mid-water and feel as though they're working and interacting in space. And NASA's Neutral Buoyancy Lab, they've got it down to a science. Full-scale models of the Space Shuttle and Space Station robotic arms fit inside the neutral buoyancy tank, so astronauts can practice their moves before they head into orbit. The full team of astronauts in modified spacesuits can work on any given project, and they're helped by a full team of divers to help with any logistics. Are there other things that you do to simulate weightlessness besides the Neutral Buoyancy Lab?
Well, the one other facility that we have, which again teaches us the physiology of what it's like to be in a shirt sleeve environment inside a spacecraft weightless, is the zero-G aircraft.
We want our astronauts to be able to train for space in the least amount of gravity possible. Now, it wouldn't do so well to keep dropping them down elevator shafts, so we've come up with a better way. Take a specially outfitted plane and fly it along this special route. On the way up, they fly very steep upwards, so you actually feel pinned to your seat with twice your normal weight. At the top, the pilot cuts off the engine and you float for about 25 to 30 seconds as the plane floats over the hump. When you hit a certain point though, you better brace yourself because you're going down also with twice your apparent weight. When you get to the bottom, you start again. Is it a strange transition when you get back to solid ground?
Yeah, there's a lot of things that go on. In space, you lose your wrinkles, you get taller, and you lose a lot of weight. And the mechanism...
Sounds like a runway
that,
model.
Yeah, exactly. The downside is as soon as you land, all those things reverse back to the normal state. We here on Earth have to have essentially check valves, little valves inside of our vascular system, our blood vessels that keep the blood from just pooling down in our legs and causing us to pass out, faint. So those basically do a very important function here on Earth to keep the blood up in our head where it needs to be so we can think and talk and see and all that. When you go to space, that mechanism is unnecessary. In space, there is no forcing function. There's no gravity that's saying you want to pull everything down to your legs, for example. So what those check valves function as effectively is really like little pumps that almost pump all the fluid back up towards your head. So if you look at people, at least for the first couple of days they're in orbit, everybody looks a little bit reddish in the face, a little puffy. All of this is part of the, part and parcel with the plumbing that you've got that's tuned to being on Earth, now inappropriately doing things to your body in space to cause all the fluid to want to go up towards your head. Thank you for watching, and we'll see you next time.